Hello? Hear me well, yeah? Nice. So Kirill is me. I came to you from Russia. I'm working there as cybersecurity researcher. I'm developing IDS signatures, analyzing network traffic, network threats, doing some researches at Positive Technologies company. There is a huge company in Russia, but I doubt you have heard about it. So today, me and you will be bypassing IDS system together. Why with netcat and Linux? Because netcat is a good tool for working with sockets, sending data over sockets, over transport protocols, and it goes with Linux by default. Some problems? So briefly about IDS systems. This is intrusion detection system that analyzes network traffic and tries to find malicious activity there, such as malware activity, hacking activity, and so on. And signatures, like in antivirus systems, are responsible for the detection. So while working on signatures, signature developer don't work with TCP level directly. If there is a special protocol parser for this protocol, HTTP protocol is a good example of that. In order to let protocol parsers do their job, IDS system reassembled transport streams such as TCP, UDP, and provides a smooth data stream for protocol parsers in order to do their job. And the network stack of your operation system does absolutely the same. So protocol parsers allow security researcher, signature developer to concentrate on the malicious activity itself, on the developing signature, and he do not think about different formats, different encodings. IDS system does this instead of him. So in the box at the bottom, you see a teeny example of such a signature. So since I'm working mostly with Suricata IDS-like signature IDS system, and all the stuff we will be discussing today is about Suricata IDS. This is open source one. And the signature is the same as Snort ones. So you see this tiny example. This is signature for HTTP protocol. It searches for HTTP post requests. And this construction, HTTP method, allows signature developer not to think about how many spaces were there before HTTP method name, in which case it was. So the IDS system extracts this field from HTTP traffic and normalizes it. I draw your attention to the fact that protocol parsers do require transport stream reassembling, good and accurate, in order to work correctly. Why so many attention for TCP protocol? Because these pictures are taken from some corporate network, and you see that more than 90% of network traffic is carried by TCP protocol. I admit you have heard about some classical bypass methods of IDS, such as reassembling issues on client or IDS sites. You may have heard that IDS cannot proceed with double HTTP encoding, non-standard ports, signature flows. So I can tell you about these methods in person later, because today we will not discuss them. And please wait a minute before I start with bypass techniques. I will tell you about TCP protocol, something you have already know. This is important. So before TCP connection is established, so TCP is known as reliable protocol, you know, yeah? Why so? Because it counts for data and it provides a correct data order. The price is 3 steps client and server do before connection is established. So client sends 2 packets and server sends 1 packet. And then a connection is established and you can transmit any data you want. So this happens every time when your browser visits a web page. They do 3 steps of TCP three-way handshake, and then HTTP protocol kicks in. So one day I was studying wget vulnerability exploit. You know this tool, wget, yeah? This is Linux tool for working with HTTP. And this is not about the vulnerability itself. This is about the way author developed the exploit. So what he did, there was a malicious HTTP content and he saved it statically in a file, payload.txt, you see at the bottom. And this file was used by netcat tool, you know, netcat. Yeah, this is tools for just sending data to network socket or reading from it. So he saved the malicious content into a file. And netcat tool has no idea about HTTP protocol. It just writes to a socket and close the connection, or read from a socket and close the connection. So again, a response was stored in payload.txt file, and it was used as input for netcat tool. Netcat was listening to incoming connections on port 80. For a web browser, for a wget tool, or some stranger. So, but then, incredibly interesting thing happened. So, instead of wget, I tried my web browser to visit this port 80. And what happened? My browser tried to initiate TCP handshake. You see the first line, packet with flag syn. And the second step is packet with flag synag, goes back to a client, but netcat didn't wait until TCP handshake was over. It pushed data right after the second packet. And then client finished TCP handshake and sent his response as usual, as nothing happened. So netcat didn't wait until TCP handshake is over and sent HTTP response before actually HTTP request was sent by client. This is how it looks in Wireshark window at the right. You see, HTTP response reached client actually before he sent the response. So does it make sense? Actually it doesn't, but this is what happened. And this is strange, but my web browser correctly displayed this HTTP response as nothing happened, nothing extraordinary. So how do you think how IDS system reacted? Of course, I wouldn't tell you about this case if it reacted correctly. Oh, yeah, of course, it didn't see this HTTP response. What do I mean? I mean that some signatures that should find the malicious data in this HTTP response, they didn't alert. They didn't see it. So if it was a correct HTTP conversation, request and response, they did. But in this case, they didn't. So what there could be instead of this malicious content for wget? Have you heard about exploit kits? Yeah. This is small pages that try exploiting some browser vulnerabilities and try to break into your computer, your system. Or adversaries could use this trick to hide a conversation between malware sample and command and control server, or any other case. So in total, from open rule set, around 5,000 signatures were affected by this issue. This is around 20–25% of overall number. But while exploiting this issue, one should fulfill some requirements. So first, you, not you, but exploit, have to send these packets, I mean a second and third row on the picture right, without a delay. So my exploit that I wrote, it sends these two packets, second stage of TCP handshake and packet with TCP data. It sends it with a microsecond delay. So this is important because the lower delay is, the higher probability that these two packets will reach the client together also across the internet, across the earth. This is important. And another problem is that some network devices do not allow you to transmit TCP data until handshake is completed. So they just do not pass it. I don't know what to do about that, but some don't. But good news is that both Windows and Linux clients accept this data. You can find my exploit at GitHub. How it works? You just run this exploit on your system, and it works as a sniffer, as packet sniffer. It listens to the interface. It do not listen to a socket, to a port, and you should disable Linux reset packets, TCP reset packets outgoing from Linux. So this is all about bypass technique number one. Going next. Where did the reset packets come from? The thing is that Linux do not know that some exploit is working because nobody is listening to the port 80, for example, nobody listening to a socket. And if someone tries to connect this port, Linux indicates that nobody is listening. Here is TCP reset packet. If port were open, Linux system did the handshake. So one day I played with my exploit for bypass number one, and of course I forget disable these packets. And what happened? As it should, Linux did send TCP reset packet back to a client, trying to connect to port 80. What happened next? Of course, my exploit was listening to an interface, it saw the incoming packet, and it sent these two packets, the second stage of TCP handshake and packet with data. And surprisingly, my Windows web browser got it. So what happened? Connection should be reset, but instead of that, Windows system did accept the data and displayed it correctly. After some investigation, I found that there is a half a second window in which I can send these packets after TCP reset packet. And this trick do not work for Linux systems, so only Windows clients did accept the data. How do you think what IDS says? What IDS sees? mean? What is nothing? So due to this TCP reset packet, IDS could not reassemble this smooth data stream. And therefore, protocol parsers could not do their job because of no stream, only separate packets. Explaining on images. Do you see these images below? Every icon is a famous vulnerability of recent years, such as shell shock, WannaCry, cost, heartbleed, image tragic. And these vulnerabilities, exploits for these vulnerabilities use TCP transport for their work. So WannaCry use ICMP protocol that works on TCP. Shell shock use DNS over TCP. Heartbleed use SSL, and so on. So what turns out that signatures for all these vulnerabilities go blind when using this bypass technique. So more than 95% of all signatures go blind. So using this technique, you become unprotected completely. So the vulnerability got its CVE number and also can be found in my GitHub. That's all for bypass number 2. A question for you. Do you speak English, right? Yeah. So if a UDP packet goes to closed UDP port, what happens? What goes back? How do you think? Huh? Cannot hear, unfortunately. But the answer is UDP protocol has no flags, and it hires ICMP protocol for this purpose. So instead of TCP reset packet, ICMP packet destination with destination unreachable type goes back. How it works? In order for client to not get lost in his own UDP packets, this payload that came from client is duplicated in ICMP message. So look at this picture. Nothing changed, just duplicates. And the direction inside of this inside of ICMP is the same as from client. So packet goes from server to client, ICMP message I mean, but inside there is a packet that came from client to server. So nothing changed, nothing hard. And yeah, a spatial ICMP code for that, destination unreachable. Do you remember bypass technique number 2? You know what I'm saying? I tried the same technique, but for UDP. But instead of TCP reset packet, we have ICMP message. So what happened? I have sent 2 packets, as in bypass technique number 2, with the first ICMP destination unreachable message, and the second is packet with some data, some malicious data. So I have 2 news for you. The good news is that indeed, IDS didn't see UDP response packet. I mean that signatures that should find something malicious in this packet didn't find. But the bad news is that client also didn't accept the data. Okay. How to bypass IDS system and not bypass client? So my idea was that since IDS system works with network protocols, dissects all the messages, and behaves as operation system network stack, IDS system is smaller than operation system network stack, and maybe some checks are not strict enough. So what I tried is You remember, yeah? So packet is duplicated in ICMP message. And what I did is I tried to change the direction inside this ICMP message. So it should be like, it should be duplicated message like from client to server, but I changed the direction like it went from server to client. Make sense? Nice. What we got? Yeah, that's worked. And operation system of client operation system didn't believe that this ICMP message was correct. And client did accept the message we sent, I mean UDP response. And IDS system believed us that this ICMP message, yes, indicates that something wrong. But as it turned out later, after the fix, the problem was in the fact that client sent UDP message to server, and server sent ICMP message back. So inner optimization logic had the flow, and all the signatures were disabled except ICMP ones for performance optimization. And yeah, I found this flow 2 years ago, even before I found the issue with TCP reset packets. The outcome is IDS systems are pretty simple. How this technique may be used by adversaries? Have you heard about DNS tunneling? This is an exfiltration technique that uses DNS infrastructure as a covered channel. Some malware samples or hackers hire this technique, and they can use this bypass technique together to harden the detection of their traffic. This is not hard to implement this feature into their command control servers, into their servers. So this is the way they can be used. So I'm finished with these 3 bypass techniques. And the common idea behind them that we use some unusual conditionals, specific behavior of operation systems that IDS is not ready for. And I'm really not surprised if not the only Suricata IDS system is affected by these tricks. So now let's take a look into the IDS system heart, the signatures. What if signatures can do harm? Sounds slightly weird, right? So this is my last bypass story for today, but the sweetest one, because this is a complete denial of service attack for IDS system. How often customers think about their IDS, about their signatures inside their IDS systems? Not often. Signatures are taken as something stable as a rock, solid, good, and nobody thinks that it can hurt. But by the way, actually, signatures have different performance. Some are slow, some are fast. And I run the open rule set of signatures against my network traffic in my corporation, and I got this performance log file. You see the top of this log file, 5 entries, and the numbers, highlighted numbers, are so-called ticks. So this is top, the hungriest signatures, and they take millions of ticks for one check. My idea was what makes these signatures, why their performance is so low. If I can find the reason, I can amplify this effect somehow. A little step aside. So what are signatures capable of? They can do many interesting things. So static content checks, regular expression checks. They can do a plenty number of binary operations like mathematics, byte jumps, byte extracting. And also it's capable of some encoding stuff like base 64 encoding, decoding. And of course, protocol parsers provide some options to the researcher. So some protocol-specific keywords like HTTP method. And these checks are often chained with each other. So you see an example of such a check. Signature at the top checks that word second goes after word first. And at the content above, it finds word second and word first and word second that goes after word first. And you may not see, but there is another word second in the beginning highlighted as black. And IDS system do not alert on this because it goes before word first. Make sense? So the logic flow I found is there is a content with 4 words first. 4. And IDS system found the first one and tried to find the word second after word first. Oh, I mixed up. So now it checks the rest of the content and it didn't find the word second. And instead of stopping further checks, it does the following. It tries the second word first and searching the rest of the content. Then, after nothing was found, it tries the next, and the next until all the words of the words first are checked. So it should stop their check before after the first check. Yeah. And in spite of number of inner limitations, I could achieve 3,000 checks on a single TCP packet. 3,000, yeah, 3,000. And do you remember, signatures are capable of regular expression checks. So let's take a use of them. So after some investigating, some research, I achieved 3 billion ticks taken for one check. So at first, the top hungry signatures took 3 million ticks, and now some signature takes 3 billion ticks. And actually, this check for one packet takes 1 second of CPU time. So by sending a special packet, a special TCP packet nearby IDS system, it checks this packet for 1 second. So usually it is 80,000 times faster. But now every CPU core checks one CPU core checks 1 TCP packet for 1 second. And of course now this flow was fixed, but how it looks like? How it can be exploited. So for that signature I found, I constructed a spatial payload with a repeatable pattern. I repeated that string 82 times and sent nearby the IDS system in infinite loop. So my IDS system had 8 cores. It used 8 cores for checks, and by sending 8 packets in a second, I took all the CPU time of these 8 cores. And what does it mean? So by sending 8 packets in a second, I gradually fill the inner queue of packets, And after some time, I can send any exploits. I can use any exploits, use any tools I want, and IDS system would not be able to detect it because it is so busy with these sample packets and it has no CPU time. So the techniques I was talking are exploiting flaws in IDS system logic, and sometimes in the logic itself. I mean, HTTP response before request, and so on. And interesting things that this may work not only with this IDS system, because I had only 2 open source IDS systems and didn't try it on some commercial ones. And also, these IDS systems are integrated in some other systems like IPFire and so on. So hopefully these vulnerabilities are already fixed in latest Suricata IDS version. Yeah, and if you're interested in what I'm doing actually, I'm working in attack detection team. We are analyzing threats, analyzing exploits, vulnerabilities, and developing signatures for them for detection. And also we are investigating our customer networks with our own product, PT Network Attack Discovery. This product allows us to investigate. It collects network traffic, stores it for weeks, and allows you to investigate how attacker broke into, what were his next steps, like if you're reading a book. So images are informative screenshots from this system, some dashboards, session cards. So that's all. Thank you for your attention. This was a pleasure for me. And I could miss some interesting points, so ask me any question you want.
The second bypass, where you send the TCP reset and then strip the TCP flow. Why Windows accept? I mean, IDS is saying that okay, reset does not work. Why does it work with Windows? What's the difference there?
The question was, in bypass technique number 2, why Windows accepts the data? Actually, I don't know. It just works. So my job is try as much as I can. And I tried it with Linux. I found it by chance. So it worked. And it worked on other Windows versions. And it didn't work on my Linux systems. So it's something about Windows network stack. Yeah, in this closet, we cannot analyze it. Thank you. Any other question? Have you enjoyed my talk?